We're live. Um, I'm seeing that. Okay. I just want to make sure that I'm seeing yeah, seeing it on YouTube as well. Okay, so thanks very much, guys, for joining us. I apologize for the change in scheduling this week, and I do realize that as a result of that, we probably have a slightly lower audience, but that's okay. We've got everything recorded and we are streaming out. Um, can the guys on Facebook post something in the chat just so I can make sure that I can see your comments, etc. And in YouTube as well, if possible, so that I make sure that I'm getting everybody. Okay. I'm going to assume that I'm getting everybody. Ah, there we go. I've got a chat from one of the sessions. I think that's the YouTube session. Okay, so let's get started now, and we shall talk about briefly last week's session. Um, in the last week's session, we covered a lot of fairly hectic binary stuff. And I wanted to know, for those who were there, how did you find it? Did you have any problems? Did you all go through the video? Give me some feedback on that before we kick off into this week's session. This week's session, I promise you, will be a little bit lighter than last week. So, who wants to give me some feedback from last week first? Any questions? Anything else? You all have microphones. Please feel free to use them.
Hi, Andrew. Yeah, I tried it. So initially it was tough. So after practicing like once a couple of times, it is okay.
Okay, so you're finding that okay, getting the concepts, etc. Anybody
Yeah.
else? Okay, I see somebody in the chat saying they took the whole week to digest it. Did you manage to digest it in the end, or have you still got indigestion? Uh, okay, I tell you what, let's kick off. Today, we're going to be talking about functions, and let me ask this of the group. When I talk about a function, what do you guys understand by what I mean by a function? By the way, I would suggest that people use their microphones rather than the chats if they're on the Zoom calls, because I can't. The people on Facebook and YouTube are not going to see the chats in the Zoom. I will read them out as they come, but it's always best if people can hear other people.
Hi, Andrew. So, function, we mean that a block or piece of code that is written to do a specific part of work or a specific work.
Okay, great. That's a fairly good um, definition of what a function is. Now, the thing about functions is basically we use them to subdivide our code into groupings, etc., and also so that we can kind of rerun bits of code without having to rewrite it multiple times. So we can put a piece of code in the function and we can call it many, many times as we need it. Functions typically take inputs and they give outputs. Well, they give outputs some of the time. Um, Whoa, I just dropped the stream. For the guys on Facebook, etc., I'm just reconnecting to the Zoom session. Something seems to have gone wrong. I apologize for that. Um, Let me just rejoin that. Um, Um, I'm just trying to get back onto the session. I apologize. Um, So we'll be back in a sec. We're just trying to get the streaming back. So apologies to the guys on Facebook and YouTube. We won't be a minute. Just resolving some technical issues here. Um,
Hi, Joe.
Hi, can you hear me now? I
Yeah,
think there is some problem with my Zoom today. I don't know what's happening.
yeah, sure.
Okay,
That's I also
we
have my.
we're back online. Joe, do you want to just drop a note um in the WhatsApp group to tell people we are back? Sorry about that,
Yeah.
guys. Technical problems do occasionally occur. So back to talking about functions. Um, as I was saying, functions take input, they give output. Well, some of the time, function doesn't necessarily have to give output, but they're there to group code. Now, what we're going to be looking at today is a variety of different function declarations um, within Golang, um, and how these functions work in terms of both their inputs and their outputs, either to take single input or multiple input, single output, no output, multiple output, etc. So I presume that everybody can see my screen okay, the video that I'm sharing. Now, we'll start with a very basic function. This little one here called basic function, it takes two inputs, two integers, a and b, and it's going to return a single argument. Now, this is just a very, very simple function. It's called basic function, and as you can see between the two brackets there, it takes two inputs, a and b, um, of type integer, and after the bracket, it has a return value that is an integer. Now, just as a note on this, you can also write this something to the effect of like that, where you've got A and B separately. We can group them if they are of the same type and in the same order. So, for example, as I had it written, A and B is int, and I could then go and add a string like that to take a third argument if I wanted to. But for now, we'll stick with the two arguments. As I said, it returns an integer. Now, you'll see at the end of the function here, I've got a return a times b. So basically, this is going to take a and b, and it's going to return those two once I've multiplied them together. And I'm going to open this quickly in a terminal window so that we can demonstrate this. Blank here. Let me just comment out all of the rest of the test code so that we can take this one by one. And if we run this, my PC is being a little slow today for some reason. There we go. So I called it with arguments 2 and 3 over here, and it's giving me a return of 6. Now, that's the other interesting thing about these functions is the fact that I can call them within another function call as kind of an argument to another function, and the argument that I get back will be the return from the function. This works well if I've only got one return. If I've got multiple returns, it gets a little bit more tricky to do that. Everybody with me so far and get this, because I need to be sure that I'm not losing anybody here, because this is absolutely fundamental. So if there are questions, please just shout. Take that.
Andrew, can you scroll up a bit where the function is?
Yeah, that's it over here.
Okay, so A multiplied by B.
Yes, and then it returns.
Oh, yeah. Okay.
One of the things to know about Golang is that if you specify that your function has a return, it will not compile unless you actually have a return. So a function that is specified as having a return must return something. So for example, at the moment, you can see I've got the little tick in the corner here that's saying this will compile okay, but if I were to do something like and take that out, I'm getting an error up here, and the reason that I'm getting an error is that I don't have a return. So the return has to match your function definition. The other thing to know is that it also has to match on type. So at the moment, A and B are both integers, so if I multiply them together, it'll return an integer. If, however, I were to tell it to return a UN16, you'll see that I can't do that because the function return has to match the function definition. Everybody clear on that?
Yep.
Okay.
Yeah.
Nice and simple on that one. The next one we want to look at is looking at a dual return. Now, I've got another function here. This one's called basic function dual return. Again, it takes an A and a B input as integers, and this time it returns two things. Now, you'll notice that in this function declaration, I bracket the returns. I have to do that if there's more than one return. If there's only one, I don't need it. But if there's more than one, I need to actually bracket that. And this is telling me that it's going to return a Boolean type variable, and it's going to return an error type variable. Error variables are interesting, and I will talk a little bit about them in a second. They don't work exactly like normal errors. Normal variables, because they're actually an interface type, but we'll talk about that. So what does this function do? It says if A and B are equal, then I'm going to return false, and I'm going to return an error. format.errorf basically just fills in a string into that error correctly within the error type. If these two aren't equal, then it's going to return whether or not A is greater than B and a null on the error. So if A is greater than B, it's going to return true. If A is less than B, it's going to return false. And the error will be null because it's already passed this. That's everybody clear on that?
Yeah.
Yeah.
Okay, so now let me go
But
and I'm just going to run the example here so that you can see that. So if I run it, it says that the result, arguments 2 and 3, because 2 was less than 3, it returned false. If I were to take this and make it 2 and 2, I would get an error. Now, notice what I've got here in terms of how I'm calling that function, right? I've got a result and an error. So if result, comma, error, colon equals, so those two are not declared variables, so I'm instantiating them at that point. Hence the colon equals. It'll give me both results. And then at the end of the if statement, I'm testing if error was null or not. Something to be very aware of here, however, both result and error here will not be available outside of this block over here because they're instantiated within the scope of the if statement. Does that make sense?
can you repeat it? It is declared
Within the scope. So basically what that means is that if I've got if something comma something colon equals, those variables that I'm declaring there and instantiating, result and error, are only available in the context of that if statement. They're basically scoped to only exist within the if statement. If I were to change that, right, to look something like this, so I've now got two variables there, and I'm effectively, let me just check. This is a Boolean. Sorry, the result is a Boolean. If I've got that, these variables are now declared outside of the if because you can see that I've changed that colon equals to just an equals, so it's using existing variables. Those variables will be available outside of the if statement. In the previous example, where I had the colon equals and I'm instantiating them in the context of if, they wouldn't be. Does that make sense?
Yep, yep.
Any questions so far? Okay, so let's move on from that then. I just want to change this code back. And we'll move on to the next one. Okay.
Sorry, can you go back to the if statement? There is
Sure.
something I didn't understand about those two arguments that are passed on to the function.
Yes.
Are they assigned to both result and error variables, and then
No. Okay. So
the condition is to the error not being null?
okay. So those two arguments are the inputs into the function. So look at the function, right? Let me just split my screen here so that we can look at it, look at the function alongside what I'm calling here. So if you look here, this is your function definition. It takes two inputs, A and B. That there is now 2 and 2, right? Then I act on A and B. So the first thing I do is I compare A and B. If they're equal, then I give it a return of false, which matches that return over there, and an error, which matches that error over there. Otherwise, I say, is A greater than B? That gives me a result to return to Boolean, and I'm returning null for error. So those are your inputs, and these here will be your outputs. Does that make sense?
Yes, now it makes sense. Thank you.
Okay. Any other questions there? Okay, let's move on. This next function deals with nested anonymous functions, effectively. So if you look at this, we have our function here called nested anonymous. And again, we're taking two inputs, A and B, both integers. We're going to return two results, both integers. So same as the other function where we've got two inputs, two outputs. However, in this function, rather than act directly on A and B, I'm creating two anonymous functions within the outer function, and I'm assigning them two variable names, effectively. So I'm now creating a variable that is a function, effectively a function variable that runs this function over here. So it looks almost exactly like a standard function definition. It's just that it's inside another function and it is assigned to a variable. In this particular case, this nested function takes two inputs, gives one output, and it'll return that multiplied by that. Same thing with the divide anonymous function, where I've got two inputs, one output, and it returns one divided by the other. If I then call these two things here, multiply and divide, and assign them into variables, I can then return their results like I've shown you there. The alternative to this, if I wanted to write this in a different way, is to actually return directly let me just comment this out. That does exactly the same thing because I'm returning an integer from the result of multiply, and I'm returning an integer from the result of divide. That makes sense to everybody?
Yes.
Any other
Yeah,
questions?
yeah, but this is clear, Andrew. But the one return the above two line that you mark now, is it why is it nested? It is inside the
Yes, you see, these two functions here will not be available outside of nested anonymous. I cannot call multiply directly. I cannot call divide directly. They can only be called from within this nested anonymous function. So they're kind of localized sub-functions. Does that make sense?
yep.
There are a couple of very good reasons for being able to do this, particularly when you start moving on to function recursion, etc., where you're going to be writing a function that is going to do recursion, and you need to basically declare the function outside of the recursive function. I'm not going to go into that in too much detail. We'll probably get to that when we start talking about algorithms, etc. But these nested functions can be very, very useful at times. Let me just restore this code quickly, just to the original example. And so that there is the basics of nested functions.
Hi, Andrew.
Yeah.
Just one on the declaration of the nested anonymous, just to understand the syntax, really. I can understand why you say a comma b and you declare that they're integers. Then the next bracket, why is it got 2 integers?
Those are
again?
the returns. Those are the returns. These are the inputs. These are the
Yeah.
returns. So inputs and outputs.
Okay. All right. Nice.
And if you look here, in the same way here, I've got 2 inputs, 1 output. 2 inputs, 1 output. That's why multiply a comma b can be returned to a single value because it's using that output. Divide a comma b, which is taking the 2 inputs from a and b and returning 1 output, which I'm putting into ret d, and then from the outer function I return the result of multiply and the result of divide.
Okay, and they have to be matched all the time.
They've got to match the declarations of the function that you're returning.
Okay, makes sense.
Okay. Now we're going to go down a little bit of a trip here. We're going to start talking about the next type of function, which is actually what we call a method, right? A method is basically a function tied to a type. So I don't think we've talked about the struct type yet in anything that I've spoken about before, so let's talk about that first. So a type is not a variable, it is something that you can make a variable of. And a type is basically, it can represent a multitude of things. In this particular case, a structure says that a variable of type demo struct is going to have 2 elements in it, A and B, right? And that's a type. It is not a variable. Please keep that in mind. So we are declaring this structure that says, here's a structure, you can go and create multiple variables from this. We can then tie methods or functions to that structure so that when we declare a variable, any variable of that type is going to have these functions attached to it. And we do that by something to this effect. And you'll see that here the declaration of this is slightly different. Because what you've got in this first bracket, so you've got a function, this ties it to a variable of this type. So ds is now going to be a pointer of type demo struct, and I'll talk about the pointers in a minute. This is what's known as your receiver. So when you instantiate a variable of type demo struct, as I'll show you in some of the other code, in fact, I'm going to pull that up alongside it so that it's easier to explain.
Hey, Andrew,
Yeah,
can we, sorry for interrupting.
no, please, if you ever have a question, please stop and shout.
Yeah, thank you. So in the previous, in the previous function, recursive function or the nested function, can we see how it runs? And also there is a question on the chat. Where is the function called? Where is the nested function called, or how is it used? I didn't quite get that part.
Okay, so yes, I can definitely show you how it's used. Yeah. Okay, so let's have a look here. You'll see here that I'm calling nested anonymous over here, right? And I'm giving it two inputs, 10 and 5. That's your A and your B inputs. And I'm getting two results from it, ret M, ret D, which are coming from the outputs of nested anonymous, right? Then inside nested anonymous, I declare two sub-functions, nested functions. One I'm calling multiply, one I'm calling divide. They take two inputs each, and they give one output each. When I call those inside nested anonymous, I call them exactly like a normal function, multiply A, comma B. So effectively, I'm giving multiply the inputs of the top level function as its own inputs num1 and num2. And that's returning one integer. Same thing with the divide, and then I'm returning the results of those two functions. You cannot call multiply and divide as they're declared here from outside of nested anonymous because they don't exist outside of nested anonymous. They are inside that function. Does that make sense?
Oh, now it does. Just that, I mean, just I'm checking my understanding. Nested func nested anonymous and multiply equal to func of, these two are two ways of writing a function definition, correct?
Okay,
Um,
so you can't declare a function, an anonymous function like this, outside of a normal function unless you declare it as a var. So if I do something like this,
what I'm asking is, can we write nested anonymous colon equal to func of a comma b integer?
not outside of another function, you can do something like this. Let me just verify that. This is declared as a var, right? So you can declare this as a global variable, right?
Mhm.
That there will work. However, if I were to do something like that I cannot do at a global level because you cannot instantiate and declare like that at the global level. You can only do that with inside another function.
Okay, got it. So the way to write a nested function within the parent function would be in this syntax, and the usual function or the parent level function
Would
will
be like
be
this.
yeah, okay, got it now. Thank you, Andrew.
And just
And
before we move off that, right, I want to show you something else as well here. If I write this, that is also valid. And that creates a variable of type multiply and a variable called multiply, and its type is set to this function definition. Then I assign this function to it. So
Right.
effectively, this just becomes an assignment. It's exactly the same way that you can do var x int to create an integer variable and then assign a value into x. It's the same thing with a function. Because what you need to realize is that if I've got a var x int, it's an integer type. You can have a function type, and a function is just another type, effectively, in this context. Does that make sense?
Yeah, it does. In this case, so for an integer variable, it will probably allocate 32 bytes of memory. And what would be the memory allocation for multiply in this case?
Well, that's a tough question. It would be 8 bytes Because it's a pointer.
Okay.
Uh,
It's a address location. That's it.
yes, it's a pointer. So it's an
Okay.
address location to where the function is sitting in the memory. That's actually a good
Yeah.
question, though. I hadn't heard that question before.
Thank you.
Andrew, what happens like if the user changes, enters a floating point or like something else instead of integer? Like will my function will return a red out?
Okay, so if you were to do this, firstly, nested anonymous, right? If I put this over here as and I try and run this, you will see that it won't run. And in fact, it won't build either. It actually will not compile because A and B aren't integers. They have to match. So you can't put floats in here because the function won't accept them and the compiler will kick it out. That's what we mean when we say that Golang is a typecasted language. The types have to match. There is the exception with the interfaces, which we went through last week. And I can revisit that at some point if you want. But effectively, to answer your question, the types have to match.
Okay.
So let me restore this quickly. Okay, so anything else before we move on from that?
Yeah, sorry. Continuing with my previous one, right? If it is a memory pointer, what does it do and how does it work? I mean, because this is not a Googleable answer. So if you would talk about it, that will be really helpful.
Well, okay. I'm trying to think of the best way to put this. So every function that you've got in any program sits in blocks of memory, right? And those functions can be called, etc. So effectively, nested anonymous is also a block of code at a point in memory, and when you call it, it goes and executes that block of code. It's exactly the same way when you declare the functions inside functions. They're just blocks of code at points in memory where you execute them. Now, we can talk about the heap and the stack, but I'd rather not do that until we get to the session on pointers because I'm going to confuse people if I go there. But effectively, as I said, these are just blocks of code, and all this is doing is giving you a place to say this is where the code is, and then you can call that code. Does that make sense?
Yes. Yeah, we'll do that at the pointer session. Yeah. Okay.
Yeah, I don't want to go too deep into that until we go through pointers because otherwise I'm going to lose people.
Sure. Yeah.
So if I may ask us to defer that a little bit.
Sure. Thank you,
Though
Andrew.
we are going to be talking very briefly about pointers here as well. Um, so moving on to the structures here. We declare this type, as I said, it's a type. When I declare this, let me just comment out this bit. And close this, comment that out. So you'll see here that I'm declaring a variable called demo var, and it's a structure, right? This is how you declare a structure. You'll also see at the beginning of this, I've got an ampersand which says, I don't want a normal structure, I want a pointer to the structure. Now, very, very basically with regards to pointers, and we're going to go through this in much more detail next week. All that a pointer is effectively saying to the compiler, my information sits at this point in the memory. So it's not the data itself, it's a location to where data sits in the memory. That's what a pointer is effectively. It's just telling you where to find the data within the memory. So I'm declaring this variable. It's a type demo struct, and as you can see, I'm filling in the elements of it there. If I want to declare it in a different way, I could have gone um, to b equals 2. Now, if I were to do this, right, what I've got there is, keep in mind I said that I wanted a pointer. What I've done here is I've declared demovar2 as a pointer variable. So that's the star. The problem is I haven't allocated any memory to that. So at the moment, this pointer doesn't point to anything. So if I wanted to do that, I'd have to do that, because that there is going to create and allocate some memory for this structure. Declared like this, the memory allocation happens automatically, right? I could also do this. Um, so all of these three are slightly different, right? The first one gives me a pointer of a structure of type demo struct and fills in the elements straight away. A1, B2, right? The second one over here declares a variable that says I've got this variable called demovar2 and it is of a type pointer. I don't filling anything in. So at the moment, that pointer is not pointing to anything. It's effectively going nowhere. I then allocate some memory for it and I fill in the elements inside the structure. With this one, I'm declaring a non-pointer, notice no ampersand there, and filling in the elements. And in this one, I'm declaring a type demo struct, again, no pointer, so it's just the data, and then I'm filling in the elements. Because this is not a pointer, I don't need to allocate memory for it. So before I continue, does that make sense to people? Speak
No.
up now if it doesn't, because I know this can get a lot of people confused.
So in this, yeah,
No, it doesn't make sense to me. Sorry, if you could come again.
Okay, let me think the best way to explain this. I think, yeah, go for it. Ask the question. Let's get all the questions and then I'll take them one by one.
Andrew, the demo var, that variable, the first one without any digit, do we have any pointer before the demo struct? I don't see that character clearly before.
That's an ampersand.
Oh,
It's that's an ampersand that says give us a reference. Yeah, Prasad
a
just put
reference.
that in the chat. So what that's saying is create a type of demo struct with elements filled into it, and then give me a reference to that, which is the pointer, and store it in demo var.
So if we say b equal to ampersand a, it is going to mean that b will contain the hexadecimal value of the address location of the variable a. Is that correct?
Yes, b will then become a Okay, so if you were to write something like int A, int B, so if you had something like this, right, var int A and int B, right, A equals 10, and then you could do something like B equals A, something to that effect.
Right. And we print
So
those.
let me just
Yeah.
put these the right way around. Just too much moving between C and, there we go. Yeah, so A and B, I put a value in A, B is declared as a pointer, and then I'm telling it that B points to A. So effectively, B is now a pointer to A. It does not have its own data. It's not got its own memory. It is pointing to A. And if I were to then print out what is in B, I would see what's in A. And if I change A, then B is also going to change because it's pointing at the same memory.
B won't change because
Well,
B
the
points
B,
to.
yeah, so B, its pointer value won't change, but its dereferenced data will.
Yeah.
So
So
I tell you what I'm going to do, right? Is I'm going to just open up a completely separate piece of code and show you this because it'll make a bit more sense. I just had another question from Facebook to explain this as well. So I'm going to do that now. I'm going to take you through this completely separately in a separate piece of code where we can look at it all in one go. Okay, so let's take it and declare a stock standard integer variable as we normally would, right? A colon equals 10, right? So A is now a declared variable. It holds the value of 10, right? If we'll make a pointer as well, a pointer, and you'll see that instead of going var a pointer and saying just int, I've put a star in front of it. That says this is a pointer, right? If I do something like a pointer equals ampersand a, that says that a pointer, which is a pointer, is now pointing at a. So a pointer is simply a pointer. It doesn't have its own actual data. It's pointing at some location in memory, and it's pointing at the location in memory held by A. And if you look at something like this, so if I print out percent %d, a pointer is percent %d, and I'm going to add a qualifier in here, and I'll explain this in a second. And I go a pointer, a pointer.
the third one should be star a pointer.
Yes, sorry, you've got to dereference that. Good catch. So let me now open this in the terminal. What you see here, A is 10. That's your normal data, right? A pointer is a pointer that is pointing to this memory location. That's where this data is actually stored for A. So that's your pointer. This is where in the memory the value 10 resides. And if I tell it that I want to see what is in that location, that's what that star does there again. It dereferences it. So it says, now go print the actual data that resides at the memory pointed to by this pointer. You can see you get to 10 again. If I do this, however, now, A equals 20, and I repeat this again, same print, right? So what I've done is I've changed A to 20. I have not touched a pointer because pointer is a pointer to A. Therefore, it's still pointing at the same memory location, and I haven't changed that. What you'll see when I run this, A has changed. The pointer is still pointing at A, so it's the same memory location, and there I'm getting the new value of A at that memory location. Does that make sense?
Yes.
Yeah.
Okay, so everybody grasping this. The thing about pointers is they sound a lot more complicated than they are. But in reality, all they're doing is saying, go get your data here, not directly from me. That's all it really is. It's simply a map to the data. So, any
So even
questions on
though
this?
so
So one,
Andrew, so even though the value of the data change, the memory space, like the location of in memory of that variable A is still the same.
Exactly.
Okay.
So
so
A resides at a particular point in memory, and it's got a memory allocation, and within that memory allocation, we put a number, 10. That memory allocation assigned to A is there, and it ain't going to change.
till what time the memory allocation will not change? Like till the program ends.
Now that's a tricky one. So if it's declared within a function, that will become invalid once the function exits and the garbage collector picks it up. So what Golang does is it says if I've got allocated memory for something and nothing is referencing that memory anymore, go clean it up and it'll free up the memory. Um, in this particular scenario, because I'm just exiting function main, this will clean up the moment that the program exits, right? So effectively, if the program still thinks it needs that memory, it'll hold on to it. If it doesn't, it won't. But it'll always hold on to it within the context of a particular function unless you remove it. Deliberately, it will actually hard remove it. And there is no way to remove within a function the memory allocated to a variable that isn't a pointer at all. So that will remain valid for the life of the function. Does that make
Got it.
sense?
Yep.
Okay, so if we go back to the other stuff, this one over here. Let me just close this off. And again, if we look here, right? So demo var says it's a type demo struct. We fill in the elements and then we give it a reference, which makes it a pointer automatically. This here declares a pointer. Now keep in mind what I said about the fact that pointers have to point somewhere, right? So if I comment this out, I'll show you something here. This is a fast way to get a crash, right? So if I've got this over here, let me just do this. And that's when I see I've got a variable here that's not okay up here. So what I've done here now is I've got this demo var, right? Let me comment that out as well, actually. With demo var 2, I've declared a variable type. It's a pointer, right? And now I'm trying to put stuff into the elements contained within that structure, right? Keep in mind the structure definition. Let me put that up. I have it here. So your variable contains two elements, A and B, right? This is a pointer to a structure like that. But because this is a variable declared as a pointer and I have not allocated any memory to it, if I try and fill those variables in there at the moment with no memory allocated, watch what happens. Okay, hold on. I just need to comment out. Something here is not commented. That should be fine. You'll see that the moment I run this, right, this will compile because the compiler says I've got a variable. You can go and fill it in, right? The moment I run it and I try and put data into that, because this is not pointing at a valid memory location, because I haven't allocated memory for it, I get a crash. That's an instant crash. If, however, I've assigned memory to this thing with the new statement over here, and I run it again, no crash. Does that make sense?
This is awesome. We used to get this same crash a lot of times in my previous project, and it used to be a big deal. And I mean, now we know why this is happening.
Yes, it's the thing about pointers, right, is that you have to know where this pointer's going. It has to have memory, otherwise you can't put stuff in there. As I said, we're going to do an entire session on pointers next week that'll go into this in a lot more depth. But for the purposes of this, what you really need to know here is that over here, I'm going to take this code out quickly. And close this off here. I create this structure and I fill in its elements and I get a pointer to it and it's assigned to demo var. Right. Now, if we go back up to the function types, which is what we were talking about here, right? You'll see that I've tied a method to this type, right? So the difference between this function declaration and this function declaration is quite subtle, right? Because what you'll see, let me split this again, is that this function here, right, doesn't start with a normal name. The name is actually after this. It starts with, what am I tying this function name to? So effectively, any variable that I declare that is of type demo struct is going to have this function called multiply attached to it, right? The DS over here, the DS star demo struct, is what's known as the receiver. That means that if I create a variable of type demo struct and I call this function that's attached to it, every element inside that particular variable will be available within the function through the receiver. So if we go back down here, and I've got demo var, demo struct, A1 and A2, right? So I filled in the elements of it. And if I then call demo var multiply like that, right? What it's going to do is it's going to call a function attached to this variable, and ds.a and ds.b are going to be these variables that I filled in over here. If I were to declare another one that said demo var2 colon equals demo struct a colon 10 comma b colon 10, and I call demo var2 dot multiply, what's it going to do? ds.a is going to be equal to 10, ds.b is going to be equal to 10, right? Because this function here, even though it's not taking any inputs, its input is the structure that the function is bound to, the type that the function is bound to. Does that make sense?
Yeah, got it.
Any questions on that? Before I continue, because it gets worse, don't worry. So if you're confused here, please say so now.
Yeah, I think I'm a bit lost here.
Okay, so this here, right, is a type, as I've said, right? Now,
Yep, yep.
that just contains multiple elements, right? So you can have a variable of that type, and every variable you declare of that type is going to contain those elements, right? This here says create a variable of this type, give me a pointer to it, which is the dereference, and fill in the elements within the structure. Does that make sense before I move to the next piece?
Yeah.
Okay. So that there means that variable. Then what I'm doing over here is I'm tying a function to the type, right? So when you instantiate this variable demo struct, you're not only filling in A1 and B2, you're also tying this function to that variable. So when I call that, I get everything that I filled in over here automatically exposed through what's known as the receiver.
We have another structure that won't be able to call multiply at all.
It won't, not at all.
Yeah.
Because it's tied to that type. But any
Right.
variable that I declare of that type will be able to call multiply, because you see demo var2 is the same type. I see Matthew's got his hand up as well. Matthew?
Oh, yeah, just a quick one. While you are explaining that, can you just go over when you use ampersand and when you use the stuff? I understand this ties to this for the pointer. When do you use ampersand?
Okay, so if I'm declaring a variable, right, var a int, right, that is declaring a as a pointer type, right? It's a pointer to an integer, okay? That's in your variable declaration. However, if I do that, where I've got the ampersand, that's saying, give me a reference to A, and B will automatically become a pointer, which is the equivalent of typing that, where B is now getting a reference to A. So basically, the ampersand gives you a pointer to something. The star is used if I've got something like, in that scenario, sorry, B, the star is now dereferencing a pointer. So it's saying, give me the actual value that is at this pointer. Does that make sense?
Oh, I see. So with this tab, you're saying just give me the value at that location. But with the ampersand, you're saying give me the location.
Yes, correct.
Okay.
So this is what you call a dereference. This is what you call a reference.
Okay, so we need to go over it again now that I know what ampersand is. Okay, cool.
Sorry, guys, I know that this gets a little bit, you know, one of the things in people I speak to about programming over the years, pointers seem to trip up a lot of people a lot of the time. Once you get comfortable with them, you'll find it's not that hard. It's just, you've got to get to a mindset of thinking that a pointer points to a location, whereas a normal variable is the data at that location, is the easiest way to put it. So again, going back here, we create a demo var, which is a structure of type demo struct. It's got elements. We get the pointer to it. This demo var automatically has this function attached to it called multiply, and ds effectively represents what is inside the structure. And so multiply can then access A and B in the context of this. If I declare it again, demo var2 is tied to this pointer that points to this version of demo struct, because demo struct is, again, remember, just a type, and therefore the multiply function will get A and B from this. And A and B in this context will be equal to 10 and 10. In this context, it'll be equal to 1 and 2. Does that make sense?
Yeah, now it does, Andrew.
Yeah,
Yes.
yeah.
Okay. Any other questions before I move on here? Just one thing. So if I run this, right, make sure, you'll see here that I'm saying that demo struct, let me just see here. One other thing. Before I talk about this demo, right, I've tied a second function to the same structure, a string function, which is effectively string, and it returns a value of a string. Now, this is it's a special case, right? And I show you this because it's really, really useful. Effectively, a lot of the Golang functions like to look for this string method. And if you call a print on this type, it will automatically call this and fill in the printed value. So if you look, when I run this demo and I've got this string method, it returns a string. So let me just make this clearer. And it's returning a string that says struct contains A colon the number, B colon the number. And it returns a string, right? When I print this, if I tell it to print it, I can call the string like that. I could also just tell it to print demo var and it would fill in that it's a string automatically. I've seen another question. After I initialize demo struct with the memory, then yes, they so the question was, is the default value of A and B equal to 0x0 after you initialize demo struct? Demo struct, if I initialize it and I give it memory, A and B will be 0. Yes, it'll initialize it with 0. But effectively, so I've tied it to the string, right? When I print it, you can see it's printing A and B, right? If I'm calling the multiply method, so I'll split again. Go back up here. I'm getting the return. So in both of these print statements, I just want to see if I can fix this a bit so it's easier to see. So in this particular print statement, I'm returning a string that's going to show me what A and B is. In this one, it's returning the multiplication of A and B on this int, right? So two different methods attached to the same data, different functions, but they've got the same data. Does that make sense?
Um, I have a question.
Yes.
Under the string method, there is a sprintf. So what does that
Okay, so
do?
format.sprintf basically says it's the equivalent of a printf, except it's creating a string instead of printing it to the console. All that this format.sprintf does is create me a formatted string.
Yeah, and that is the return value of the method string, and that's what gets printed on the console. No, I'm kind of lost here in the string method.
Okay, so effectively, if you imagine a normal function, right? Make it no return, right? This function here is going to take A and it's going to print it, right?
Correct. Yeah.
Print it to the console. But if I do this, I'm not printing anything. I'm creating the string that I would print and I'm returning it. And then the return from this function I can then print out. So the difference between a printf and an sprintf is the one creates a string that you can pass around, stick in a variable, return, whatever, whereas a printf actually puts something out onto the console.
Where would this kind of scenario be used, Andrew?
With,
I mean, we could have simply printed out from here itself.
okay, so imagine, for example, that you've got 10 different functions and you want to run a function that's going to give you a string that you're going to use in something else, right? Rather than necessarily printing it. Remember, strings have got a lot of applications beyond just printing them, right? So you might want to create a string that you're going to create half the string with one function, half the string with another function, and then join them together later. That means that you're going to need two string returns from the two different functions into the main, where you can then join the strings together.
Yeah, makes sense. And file write operations or some such.
Exactly.
Okay, got it.
Yeah, thank you.
Okay. So that's the string method that returns a string, that returns an integer, and they both have access to the same data. Now, keep in mind what I said, that these two functions, right, are acting on the data inside that structure. So if I take these two lines and I duplicate them, and what am I doing here? I'm changing the values that I originally initiated with inside demo var. And then I'm running the same two functions on the same print again, right? You'll see over here that in the first instance, struct contains 1 and 2. If I multiply them, I get 2. In the second instance, struct contains 5 and 10 because I've reassigned them. Multiplying them is going to give me 50 on the multiply method. So those methods are tied to what is inside that structure. Does that make sense?
Yeah, it does.
Yeah.
Okay. Any questions? Because I want to be very sure we are clear on this before I move on, because the next bit gets even more complicated.
So the one that does this magic is this receiver part of, I mean, on the function for multiply. It's what makes them getting tied together when we giving the inputs.
Yes,
If I'm correct.
effectively, yes. The receiver is what contains the actual data.
I get it. Thanks.
Yeah, Andrew. So when the struct is defined, so it gets initialized with values 0, 0, A and B.
Yes.
And then when the values are passed in with ampersand 1 and 2, those values are going to overwritten with the 1 and 2. And
Okay,
then
so the ampersand doesn't pass in the values. The ampersand simply gives me a pointer to the structure containing 1 and 2. The ampersand is merely to get me a pointer. If I were to do this, right, that's exactly the same thing. This here is the actual data with the elements. Demo var is a pointer to this data.
Can we do a demo x dot a, demo x dot b?
Yes, you can.
But why are we not doing that? I mean, you went through the whole pointers and thing for referencing it and calling all those, using all those variables and the functions. So, is there any specific reason why you did that?
Why I used the pointer, right?
Yeah,
So
instead of the straightforward variable name itself.
that there, right? If I call that, let me just see something. That there can work, right? Where I'm not using pointers, but I'm going to show you the difference between a pointer receiver and a non-pointer receiver in a second in the next section. There is a very good reason to use pointers as receivers. The primary reason is the fact that if I ever need to fill anything into DS, right? So I could, before I return this, do that, right? That's going to change the value in the receiver. Now, if I run these, so in the first instance, I'm trying to think about this. If I take this and I make this a non-pointer receiver, it doesn't change this coming out. This becomes a reference. It copies it effectively. It's going to be easier to explain once I get to the next section on this. But my general rule is that if I'm going to be using a receiver, I want them as pointers, purely because you cannot assign data to a receiver. You can, however, assign data to the memory pointed to by a receiver. And you'll see it in a second when I get to the next section.
Okay,
Bear with me.
no problem. I know you have your valid reason, but I just wanted to know. So
Yeah, I'm gonna try and no, I'm gonna try and get to that in a second, right? And you'll get a clearer indication of that in a minute, right? But does this make sense what I'm saying about the fact that the ampersand doesn't actually assign? The ampersand merely gets a reference to what is assigned over here.
Yeah.
Okay. So, everybody clear on this? Because things are about to get complicated. Okay, now I'm going to look at another type. This one is a slice of integers. And you'll see that I've called this a slice receiver. Now, at the moment, as that is declared right over there, let me just take this bit out so that I can comment this. And this here, this type slice receiver int, if I have something like var a int, that is declaring a variable of type a that is a variable called a that is a slice of integers. Var b slice receiver is almost identical, right? They're both slices of integers. The difference is that because I've declared a type here, I can assign methods to it, right? I cannot tie methods to this. I can tie methods to this. Does that make sense?
Yeah.
So slice receiver is basically a type of a slice of integers. Nothing more than that, right? Now, we get to why we use pointers, right? If I do something like this, a equals append a comma 10, that's going to shove 10 onto the end of a, right? Makes sense. So I'm appending 10 into this slice. With B, that is a slice receiver, when I tie a method to it called append, right? I now need to add to this variable. So I can now go B, var B equals. I need to, by the way, declare memory for that. Otherwise, the function doesn't even exist, right? So I'm effectively, well, actually, I can, yeah, that's fine. So now I've got B that is a pointer to this type called slice receiver, right? If I call B dot append 10 and I print out B, need to dereference B over there because it's a pointer, and I run this, you'll see that B contains one element, 10, right? And I could actually go and append more to it, like that. And now B contains 10 and 20 when it exits, right? So effectively what append does is it's putting stuff into this receiver, right? But watch this. If this is not a pointer, and I have something like for B slice receiver, that's fine. You'll see that I've now got an error over here. And effectively it's saying, wait a minute, you can't actually call this, right? Firstly, B may be null, so let's just actually put something into that slice. Make int comma 0. So that way B is now a slice, it's got something in it. I can call this, right? Not a null slice. However, it's not going to compile because one of the rules with receivers is that you cannot assign back to the receiver. So what will happen here is if I try and run this, it'll tell me invalid indirect. Sorry, let me just remove that error there. You'll see that when I'm printing B over here, it's not doing anything. It's not appending because what's happening here is I'm putting the data into a copy of SR because I'm not accessing the memory at the base. So the moment I'm touching that receiver, if I'm not dealing with memory that is pointed to, the memory becomes local to the function. It'll shove something in there in the append. The moment the function or the method exits, the data's not being passed out. That's why you're using the pointers. Does that make sense?
Yeah, Andrew, just to access the memory.
It's so
Uh,
that you are actually accessing the right place when you're putting the data in. Questions? Getting silence. Everybody okay with this, or have I confused everybody?
the three
Yeah.
dot just represent the slice.
Okay, so that's something else I was going to come back to, but let me talk about that now. That's effectively a variadic, right? Basically, what that says is that A can be passed into this function either as one integer or 5 integers or 10 integers. It expands it. So if I here go B10, as you could see, let me just put back the pointers over here. If I run this at the moment, you can see B is appending, and I run this, you'll see that B is now equal to 10 and 20. Those 3 dots allow me to do this. And you'll see that I can put in multiple arguments. Now, the rules around variadics like this is they have to be the last argument accepted by the function. So I could not do something like that's invalid. It has to be the last argument. You can put anything before it like that, so long as you've only got one variadic input at the end, because otherwise it's not going to know how to parse it, right? Now, the other thing about this, right, is that you'll see that I've got if len a. That's because effectively in this particular case, it's passing in a slice. So it will pass in all of these elements as a slice, and a will become A0, A1, A2, A3. If you look at this function though, that when I call that append, I tell it dot, dot, dot. That says expand the slice again into a bunch of variables. So it's an expansion. That there takes a bunch of variables of a slice, that expands a slice into a bunch of arguments.
Thank you, Andrew. And what does the make function do? I'm sorry, I don't know this.
Okay, so if you look, var b over here is not a pointer, right?
Mm-hmm.
B, remember, it's a slice. So a slice can be variable length, right? And that means that you've got to have memory even at a reference point, right? Make basically just allocates for that slice in this particular case at a reference point. So the difference between var b equals new versus both of those are going to allocate me an empty slice effectively, right? However, this one here is going to create me an empty slice, and C will be the actual data within that slice, right? It'll be the actual slice. This here will create me an empty slice, but it'll give me the pointer to that empty slice. So make effectively is allocating memory. If I were to do this,
Make allocates memory, however, new creates a pointer to the slice.
yes, correct.
Okay.
So that says make a slice of integers and we'll make it a type of slice receiver. Now you see this 10 here. That's allocated memory for 10 positions within the slice, right? So watch what happens when I run this now. There's my 10 positions. They're all zeros. And then I've added this to the end of it. This is why I normally do that and make it a zero at the beginning. It just depends, you know. Append will add to the end of the slice, and but you have to initialize that slice to do this. And whether or not you initialize the slice with nothing in it or 10 things in it, up to you. Does that make sense?
Yes, and there was a point. There was a point where you had star b in the printf statement. So what were we trying to do then?
That dereferences the slice itself. So if I look at this, right?
Yeah, but we are already getting print values of the actual values and not memory location. So what is the difference?
Okay, so if I do new slice receiver and I print it like that, right? What you'll see here is that printf is being smart, right? It's printing that this is a pointer and here's the data within that pointer. If I dereference it, you'll see that I get the actual data. So B is a pointer here. Now, what's the difference is this. If I have something like so that's my non-pointer and I append to it, right? I can do something like this. And that's going to print me whatever's at the first position in that slice, right? Prints 20. I'm trying to think why it's... Oh, I added this extra argument, so it was ignoring the first argument of what I was passing in there. But there we go. So it prints 10, right? That's at position 0. If I change it to 1, it's going to print 20.
Yeah.
Now, watch what happens if I've got a new slice receiver and I run the same thing, because now B is a pointer, right? You cannot index a pointer. So that will not work. That's one of the major differences. To actually get to that value now, I would have to dereference it. So that I can get to the data itself to index it.
Yeah, now I understand it. I'll listen to today's class once again probably, and then it'll all register. Yeah. Thank you, Andrew.
Sorry guys, I realize that this is quite tough going, but as I said, questions, there's no such thing as a stupid question. You just got to ask, you know what I mean? And I know that there are people who struggle with this, but guys, please, if you don't understand this in the week coming ahead, contact me, WhatsApp, Facebook, the YouTube comments, whatever, right? Because if you don't get how these methods, etc., work, you're going to struggle going forward because this is so fundamental to so much of what we will go into going forward. I think I have one last function for the day, and then we will break and you guys can sit and kind of contemplate it and we can take questions, etc. The final function that I want to show you for the day is this over here. I think I still got an A declared somewhere here. Da, 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 da. Okay, well, let me just get rid of that, and I've got something commented somewhere. I just got to figure out where I left my comment in. There. Okay, so remember over here, I'm making it, and over here, this here, by the way, is over here. This is a slice receiver. It's not a pointer, right? Keep in mind I need the pointer. So I go and grab the pointer. I call the append. It's going to fill in whatever's in A, right? Because here I'm using A as a pointer and I'm appending on the method because the slice receiver takes a pointer. Now, this next function could scare you all, but please don't let it. Okay. So, remember what I said about not being able to index a pointer. You have to dereference to be able to index it, right? So what I wanted to do here is take a slice containing 1, 2, 3, 4, which I'm putting it in it over here, right? Then I want to tell this function over here that I want to delete the element that's sitting at position X in the slice. So in this case, 1 would be position 0, 2 would be position 1, 3 would be position 2, and etc., etc. It's probably easier to understand if I simply fill in the positions like so. So in this case, if I say I'm going to delete X and set X as 2, 2 is going to disappear out of the slice. Right. How am I going to delete 2, which is in the middle of the slice? Now, in this particular case, I've said I do not care about the ordering of the slice. There are ways to do this to preserve order, but in this case, I don't care. Hence the name of the function, delete element, no order. Right. So what do I do here? I say, what is the length of the slice itself? -1, because remember, it's 0 based. And I say here, okay, is this length of this slice going to be sufficient such that I can actually get to X? Because if X is larger than the length of the slice, I'm going to be referencing an element of the slice that doesn't exist. So that tests that X is actually a valid element I can delete, right? The next thing I do, keep in mind I need to index, so I dereference the slice over here, and I say take the element at position X and take the last element of the slice and make them such that the last element is the original position X, and so the original position X becomes the last element becomes X. So I swap those two parts of the slice around, right? Then I simply truncate the slice, because I'm now saying this slice is equal to the original slice, but only up until the second to last element. What I end up with by doing that is I've just deleted that element out of the slice, and effectively I've removed an element in the middle of the slice in the most efficient way possible. Does that make sense?
Yes.
Questions?
Yes.
So let me run the code, and you can see here I've got 0, 1, 2, 3, 4 in the slice. I'm deleting element 2, which is this one over here. Remember, 0, 1, 2. And it takes 2 over here, and it swaps it with 4. Hence why 4 is now in where position 2 was. And then I truncate the slice to remove its last element. Questions?
Okay, just leave it over there for a moment. I just wanna go through the syntax.
So this is basically similar to, I think, what we did in session, I think, 1, whereby we were deleting an element from a simple slice. But now, in this case, we're using pointers to do so.
Yes,
I think,
we're using pointers, and we're deleting from the middle of the slice without caring about the order.
yes, I think I get it. Yeah.
Any questions? You see, the thing is, the reason that I'm dereferencing here, right, is because keep in mind, I want to delete from the slice that is a receiver. So remember what I said earlier, I have to pass it in as a pointer, otherwise I'm not going to be touching the data when it returns. I'm going to be touching a copy of it inside the function returns, I'm not going to get the original slice back, right? So I take it in as a pointer, but I have to dereference the pointer to be able to index. And over here, I have to assign the newly truncated slice to the location pointed at by the receiver. That makes sense to everybody? Okay, so I just had a question. Is pointer
Yeah,
Where on the
similar?
function are we swapping?
Right over here. We're swapping over here. Element 1, element 2, effectively, this is the element X, right? This is the last element. So call them element 1 and element 2 is equal to element 2 and element 1. So this here is a swap in one go, because this first part of this equals will be equal to this first part over here. The second part will be equal to the second part. So this becomes the last, this becomes X. That does the swap. Make sense? It's the equivalent of this, right? If I go A comma B equals B comma A. That will swap A and B. So A and B will start out as 10 and 20 and will become 20 and 10.
Well, what confused me rather is that in that swap statement, there's no apportionment at all. There's no equal sign. I don't see the assignment. I just see
Over there,
elements listed.
right there.
Oh, sorry, it's my resolution. Sorry, I thought that was a minus. Okay, let me make it smaller. I don't know. Okay. Oh, that's an equal sign. Okay, all right. Okay, no, that's me. Sorry.
I had a question in the chat. Are pointers similar to C, to C programming language? So pointers in C and pointers in Golang work very much the same way. There are a couple of differences which I will go through in our session on pointers next week. Primarily in C, you can actually increment a pointer itself to get to another value. You can do that in Golang, but it's a lot more complicated to do because it's dangerous when you start kind of changing what pointers are pointing to mathematically. So they want you to think very, very carefully about doing it. There are ways to do it, and I will cover them in the next pointer session, but that's pretty much the only real difference. There are some differences with regards to the fact that Golang has a garbage collector, which means if you assign memory to a pointer, but you're no longer using that pointer, Golang can clean that up. And then you've got to be a little bit careful that you don't end up in a situation where you think something is still pointed to, but it's gone. Whereas in C, if you assign memory to a pointer, unless you explicitly free it up, that memory will be locked and you'll end up with a memory leak. So I hope that makes sense, but we'll get into it in more detail next week. So, everybody okay with this? Any more questions, either from YouTube, Facebook, on the Zoom channel, etc.? I don't want to kind of move past anything further on this week because I need you guys to be sure that you get this before we move on to the whole section on pointers. And your homework for the week, similar to last week, where I said to you guys, go through and understand all of the binary, is to go through this code. Go and download the example code that is on the GitHub repo, right? Play with it. Modify it. Write your own functions that use the receivers and the structures. Play with the types. Come back, show me what you've done. You know, let's see who can be the most creative with what they've learned here. So what I want you guys to do is go away and write something interesting with what you've learned, and next week we'll see who's managed to do the most creative thing with it.
That would be
Okay.
interesting. Yeah, sure.
By the way, just one other note about functions and taking things in, right? So we talked about methods over here and normal functions. Okay, so I just had a question from Facebook. By the way, apologies if I have a bit of lag responding to Facebook. I think the questions are slightly delayed because of the stream. So I had the question of, don't you have to store X in a temporary location before swapping? One of the nice things about Golang is no, you don't. Because in a statement like this, it figures that out on its own. So effectively, as I said, over here, X will become last, last will become X, and it handles that. I don't need temporary locations to actually do that. I hope that answers that question. The simple answer is no. It just works. It's quite cool. As I was saying though, one of the things about functions, if you look at this, right? A and B in taking in an int and returning an int, right? If I were to write a function and do star return star A times star B. Okay, that says return an integer from A and B that have been dereferenced to get the integers and multiply them together. Right. Here's the big difference. If I over here go A equals 10 and B equals 20 and I return this as an integer, right? A and B are being passed in. I change them, I multiply them, I return the value. A and B, however, are passing in actual data. So if I call basic function, I'll show you the difference here. Okay, so, sorry, got a dereference. And at the end of my demo code over here, I will go x equals 15 and y equals 20. And if I call the first one, xy. Okay, so that's going to call basic function with x and y, right? Of 15 and 20, but it's going to ignore the 15 and 20, and it's actually just going to use 10 and 20 over there, and it's going to return the result, right? So if I run this, returns 200. 10 times 20 is 200, right? And what you'll see here is that x and y are not changed because I'm not changing the stuff at the pointers. Those A and B are being passed as data. This is setting data. It's not changing the original, right? However, if I run the second function, sorry, I've got to pass it pointers. So I'll just get references over here. What you'll see is, hang on a sec, pointed to x is 15 and 20. You'll see now that x and y have changed their values. Does that make sense as to why that's happening? Or have I just completely lost all of you?
Yeah, makes sense because we have in the second function we have passed a pointer. So pointer, so accessing those pointers we can actually change the value. Rather in first function we cannot change the value of that memory location because we're not passing the pointer.
Exactly. And there are many instances where you may want to pass something into a function and change the value and then get it back without a return. Because keep in mind that if I do this over here, right, with this, I'm effectively having to make a copy of A and B and then return it. Over here, I'm just passing a pointer and then modifying what's at that pointer. This function here is going to be less intensive than that, CPU-wise. No memory copy. That makes sense?
Yes, that
Yeah.
makes sense, but I feel like at some point, the first function can also be safe in programming in terms of
Definitely.
reusability of the code.
Okay, so there are definite, when you start playing with pointers, there are definitely safety issues at play, right? Particularly when we get to the probably 2, maybe 3 weeks from now, when we start getting to concurrency in code, right? And we start dealing with things that are running in parallel in threads, etc. You've got to be very careful what you start doing with pointers, because you can change the value referenced by a pointer in one function, access it in the other function, and not realize that it's changed. Pointers allow you a lot of flexibility and a lot of optimization, but you've got to be careful. So you are correct that the first function is safer than the second function, but there are definite cases where the second function has applicability.
Yeah, true. There's a kind of trade-off, I think, but yeah, I get the point. I understand that.
Yeah, there are definite trade-offs as to where you use pointers and don't use pointers. I would never ever suggest to anybody that it's a good idea to write a multiplication function in the way that this is written in standard course. I'm using this purely as a demonstration. For standard functions like this is the right way to do it. But a function like this does have purpose, as you'll learn when we start talking about pointers in more depth.
So tying this back to our structure and the function we used with it, is there any specific reason?
As to why you would use a pointer over here?
In the structure.
Okay, so okay, so in this particular case, the structure itself isn't, but the elements here, well, this is a type, remember. So the structure could be a pointer and the elements inside it may not be pointers. There are a lot of cases, but as I said, this is going to be easier to explain when we go through,
Okay.
in more depth, because there are some very, very interesting things that you can do with pointers. One of the things, for example, is if you look at something like a UN32, right, which is a 32-bit integer. Remember, computers think in terms of bytes. So 8 bits, 8 bits, 8 bit, 8 bits. Well, and they go lower than that, zeros and ones, but most things are referenced as bytes. So a 32-bit integer is going to be comprised of 4 bytes, right? So if you've got a slice that's got a whole bunch of numbers, one after another, a whole bunch of bytes, 8 bits, 8 bits, 8 bits, you can use a pointer to point at a position in that slice and tell it that the next 4 bytes are actually a UN32 and fill in your UN32 from those byte values. That is where things start getting interesting, because that is effectively how you end up decoding network protocols and various other binary data. Because remember, when you read data from a file or a network card, it's going to come in as a string of bytes. And you need to convert that into readable data. That's where your pointers start getting really, really useful. But I'll show you that next week.
Sure, Andrew. Thank you. I hope you don't feel like a doctor teaching alphabets to kids.
No, believe me, the way that I look at this is that I watch a lot of university graduates coming out of university and they've been taught C. And what really scares me is that nobody's really given people a solid understanding of pointers, because in a language like C, pointers are absolutely, absolutely critical. In a language like Golang, you've got the option to use pointers, not use pointers in many cases. There are certain things that you really need the pointers for, but pointers and programming are fundamental. It is one of the fundamentals that in my original talk on programming fundamentals, I said to people, you need to learn the fundamentals. Well, pointers is one of those fundamentals. You've got to understand the difference between accessing data at a particular point versus accessing that data by something that points to it. Because when you're passing data around, you've got the option to copy that data into a function so that it can access it, or use that same data from multiple functions at the same time by accessing it via its pointer location. And really, if you can grasp this pointer stuff, and I realize that it's not the easiest thing and a lot of people struggle with it, I promise you now it'll make all your other programming a lot simpler. Which is why I'm doing an entire session on pointers next week. But I hope that what I've given you this week has made certain things a bit clearer. And as I said, if you've got questions, please ask, because you're really going to need to know this stuff going forward. So don't feel like I don't understand this, but I don't want to look like an idiot by asking. There are no stupid questions, only stupid answers. So ask if you don't understand. WhatsApp, on the Facebook group, on the YouTube chat. I watch all of them during the week, and I will respond as soon as and as promptly as I can. So I really hope that I have helped some guys here. And yeah, as I said, the videos are up on YouTube and Facebook. The YouTube video will probably go down in a couple of hours briefly while I edit out the drop in the Zoom session out of that video, but otherwise it'll be online. And as I say, you guys can get hold of me, ask any questions, but spend a week playing with the code. It's on there, it's on the Golang repos. And for those of you who don't have that Golang repo, I'm going to just paste that again in the chat for the URL for it. So I've pasted it in both the Zoom chat and the online chat, and I will also then take that and I will add it to the comments on the video itself. And you guys can play, and yeah. So any final questions before we end for the day? I realize this has been quite a long session, but hopefully you guys have learned something from it.
Yeah, Andrew, enjoyed a
Yeah,
lot.
we have learned a lot actually.
Yeah,
Yes, and it needs a lot of practice also.
okay, great stuff. And like I said, please go and play with it over the week and contact me if you need anything.
Yeah. Thank you for spending this valuable time with us every week, Andrew. And this is really, really helpful to learn a new language from the basics. And it's not only about the language, it's about a lot of concepts lying underneath. And I'm thoroughly enjoying all these sessions, each one of your sessions. So thank you so much.
Thanks. It's great to hear that. I enjoy these sessions as well for myself, because one of the other things I'll also say to anybody is once you know a language or do something every day in your day job, you often find that some of the things that you kind of do in your head all of the time, you don't even really think about how you're doing them. And when you go back to doing stuff like teaching, like I'm doing now, and it's been a learning experience for me, you've actually got to go and revisit those concepts yourself. And you pick up things from doing that you think, well, I could do this slightly better, etc. So even the teaching is a learning experience, and it also reinforces it in your own brain. I'll say to anybody that if you've got friends who want to learn Golang and you want to embed the concept of these last couple of videos in your head, take the videos and teach the videos to somebody else yourself. Because the day that you teach it is the day you'll never forget it. I promise you now. So just something to think about there as well. Don't be afraid to teach in order to embed in your own brain. It works.
Yeah, that is very, very true. Thank you. Thank you for, saying that use the video to teach as well. So,
Yeah, no, great stuff. And thanks again to our host, Joe, for the Zoom session. Much appreciated. I'm not sure if Joe's around at the moment. But yeah, we'll call it a day. And as I said, I'm available to take questions, comments, anything else. So thanks very much.
Yeah, thank you.
Thank you.
Thank you, Andrew.
Thanks. Bye.
Thanks.
Thank you, Andrew.
Cheers.
Cheers.